So in this video, we'll be talking about computer programming, its history, what makes up a programming language, while we use them, and show some examples of actual short computer programs. So what exactly is programming? Well, an algorithm is a sequence of steps or instructions for a computer to perform a task, or actually the general sense of it means for a person to perform a task. Computer program is the implementation of that algorithm. They allow computers to perform repetitive tasks with a high degree of speed and precision that's impossible for humans, although the earliest computers humans could compete with in certain ways, but now it's billions of calculations a second. It's formal and that there's a formal structure, a formal way of writing a program. It's unambiguous. Each instruction does a specific thing. It's deterministic. Everything it does is predictable with zero chance of randomness. Well defined. There's usually clear documentation of every facet, how it works and how to use it. Lastly, executable in that the instructions can actually be executed in the implementation. An algorithmic structure is that everything is built step by step with specific instructions to follow. It has a formal syntax and grammar, and everything in it has meaning and semantics. I really should say meaning or semantics. So every symbol has meaning. It provides some degree of abstraction layer between the hardware and the programmer. It allows for states to be manipulated while the program is running. This simply means that data associated with the program can be stored, changed, and updated during the program's execution. It has control flow so that a program can branch off as various conditions are met, and it's modular. You run what you need to achieve your goal instead of needing to use everything. You're not going to have to use every function, every piece of a programming language. Back in the days of mechanical computers, if it was programmable, it might involve something like changing gears or gear ratios. Early computers like ENIAC required physical wiring. You'd actually run cables and patch particular panels. You'd set up individual function tables. You'd manually input values through switches or the connections. And then you'd get output as either lights on panels or punch cards, actually a mixture of both. Then the punch cards would have to be further processed by a tabulator to get a clear printout. Programming provides a certain level of abstraction between the physical hardware and the programmer. In some cases, it's actually even multiple abstraction layers. There is a difference between high and low level programming and how much abstraction there is between the user and the machine. Generally speaking, we say that assembly is the lowest level as it's just one step above the machine code, although there will be people that argue that one. All right, so you may have heard of a Turing machine, not a Turing machine, but a Turing machine. It's an abstract machine, meaning it's really just a thought process without necessarily needing a physical machine. It was proposed by Alan Turing in 1936, who is often considered the father of computing. And yes, there will be people who argue with on that one. It starts with an infinite tape, and the tape is divided into individual cells. Think of it like computer memory input and output. There's a finite set of states the machine can be in. Additional states have to be added to the machine. The machine itself can't simply create new ones. There's a finite alphabet of symbols which can be read from or written to any cell on the tape. There's a set of rules which determine what symbol to write, which direction to move, and what state to enter next. The alphabet can technically be any set of symbols and can be something incredibly simple. I think you could do like 0 and 1, A and B, whatever. It could be any digits, characters, but it must be an established finite set. The machine can't simply create new ones on the fly. Now, an important detail is there's technically no true Turing complete computer or anything, as everything has finite resources. So technically, everything would be a finite set machine, but we still call it Turing complete if it satisfies everything else. This is not just a computer thing. This applies to computers, microcontrollers, processors, programming languages, anything that satisfies all these conditions. Just a kind of a short history of programming. In the 1940s, early computers had to be completely wired by hand, values had to be inputted manually, and new programs required literally physically altering the machine. That could take days or even weeks in some cases, assuming no problems in the middle. As like ENIAC went through vacuum tubes like Tic Tacs. The late 1940s, though, early 50s, you got to a point where instructions could actually be put in and fetched from memory and consisted of, binary instructions. And programmers need to know everything about the computer's hardware, but there was a lot less wiring at this point. Eventually, by the 1950s, you had assembly language, which introduced mnemonic names for machine instructions that could be translated to machine code. This did not make it a programming language in the sense you'd understand now. It just started with shorthand written on paper for each kind of instruction. Then you would consult another piece of paper for how to wire things up or put in machine code. But then within a few years after that, you started to basically you had your first high level languages, mid 50s to the 60s. Fortran came out, COBOL, Lisp, but you also had things called Flowmatic, Algol, IPL, a lot of languages that aren't still used, but there's still somewhat modern versions of Fortran, COBOL, Lisp. 60s to 70s, you got newer languages that were highly structured, and you got upgrades to all the existing ones. And then you had new languages like BASIC, Pascal, and C. The 70s was all about the C revolution, where you had the rise of C and C-based languages, which created an even bigger standard and combined both low-level and high-level functions. By the 80s, you had interactive development environments. You had so many more easy ways to learn how to program and to implement programming, and this is when the PCs really took off. Now, a lot of people compare humans and computers. Sometimes they'll say humans are dumb, computers are smart, or they'll say humans are smart and computers are dumb, and both can be true in certain cases. Humans are prone to mistakes, and this also translates to computers. A computer doesn't make an error directly, except as a direct action or inaction by humans. You've heard of the thing that all errors are user errors, and in a way, that's right. A computer itself cannot screw up. A broad goal of computing is to make it actually function more like a human to some extent or another and perform human tasks at really high speed and precision. A human can probably solve a math problem maybe once a second. A computer can do billions of those a second, tens, hundreds of billions at this point if you combine everything in your computer. However, humans can perform a number of operations at scales of magnitude that humans can't. Humans can recognize specific symbols or people, even with great variability in appearance, and that's a really powerful thing. Computing is obviously crossing the gap. I remember a time when optical recognized characters was still not super practical, and now you can have computers read thousands, millions of types of handwriting that recognize most of it translated, etc. So the gap is closing, but there's still a lot of things that humans can easily do that computers can't. Now, I've talked about hardware abstraction. With no abstraction, the user is directly working with the hardware, wiring, rewiring, flipping switches, reading panel lights, etc. Basically, what was done with ENAC. It would require users to know literally everything about the computer. Reprogramming could take days or weeks with big computers. A few years later, computers could start to store instruction steps in memory, which heavily reduced the need to wire, although that was still needed for some things, like maybe wiring to switch instructions. Assembly just started out as a way to write things out on a piece of paper before you translate it to binary code, and that's changed over the years as well, although it could still be used that way, I suppose. You were still having to flip switches or input things versus punch cards or punch tape, and you would have to translate to binary. Eventually, you had the first programming languages. Fortran allowed for programming that could focus on engineering and math. instead of the need to program and assembly machine code. COBOL did the same thing for business and data processing. The syntax and the grammar of the language was more human. It required less knowledge of the hardware to actually program the computer. Eventually, compilers came along that could translate the programming into machine code. That allowed for certain languages to be used on more types of computers, including, like Fortran and COBOL, and then some of the newer ones. Now, we're going to be talking about compiling and interpreting. Well, compiling is conversion of human readable programming language into machine readable machine code. Some languages compile the entire program before it can be executed, and others interpret instructions in real time as the program is executed. While most languages are sort of technically divided into compiled or interpreted, there's plenty of things that are both compilers and interpreters sometimes for the same language. We also have JIT, which is just-in-time compilers. They're sort of a middle ground. They compile instead of strictly interpret as the program is executing. Compiled programs tend to be faster as constant interpretation takes additional steps, resources during execution. The act of compiling, though, takes time and resources, although actual program execution may be relatively quick depending on the complexity of your program. Cross compilers compile code on machines different from which it was coded on. That's an extremely important concept as computing went on. Native compiler compiles code on the same type of machine and operating system that it was coded on. That would probably be how you describe some of the first compilers. Bootstrap compilers, they're coded in the same language that it's compiling from. And then there's transpilers, I can never say that right. The source-to-source compilers basically translates from one programming language to another. So there's various qualities of programming languages, and this is not even remotely a complete list. Starting with something that's imperative, it means it does this, does that. You basically could tell the language exactly what to do step by step. Procedural means it programs are broken down into reusable steps, functions to do specific things to data. Object-oriented organizes the code around objects, which bundles both data and behavior. You can think of a car having properties like color and speed, and then it has methods such as drive and brake. Functional programming, it tries to avoid changing the state. So instead of modifying a thing, it simply creates a new one of the thing. Logic programming programs are written as facts and rules, and computation is done by logical inference. Reflective programming means it can inspect itself and modify itself while it's running, usually to make things more efficient. Standardization means that the language has actually been formalized and standardized by some kind of governing body like ANSI or ISO. Generic programming means it can use templates and type parameters, and that the code can basically work with any kind of data type. Now, we also have something called pseudocode. Now, this is an actual programming language, but it's an idea of breaking down what you're actually looking to do. In a way, this sort of shares something with the oldest method for assembly. Instructions are written in words, resemble actual programming statements to some extent, basically break down a task for individual instructions. You can start with just a basic descriptor and then just start um, grinding that down. It can be a standardized implementation. There's actually guidelines for good pseudocode, or you can just casual parlance, depending on your audience, your intent. It's really just one aspect of program planning, depending on the complexity of the program. You can start with as simple statements as you want and go through stages of just converting it into simpler and simpler, more specific instructions and flow a little closer to how you want to implement it. So you might start with light each LED in a sequence for 1 second and then turn it off, light the next one for 1 second until all 8 have been turned on and off. I can convert that for each of 8 LEDs, turn on, wait 1 second, turn off. The second is going to make a lot more sense. You're developing a for loop in a programming language. Now, we also have a thing that's usually called a convention. It's usually an accepted guideline that recommends a certain style, practice, or method. Something may work just fine without using that convention, but a convention makes it easier for others to read both how the program operates and how it should look in the actual code. But there may be very good reasons for breaking convention in some part of a program, and there may be multiple guidelines that vary or conflict with each other for the same thing. There's also commenting and documentation. Documentation for users should tell the user how to use the program, including various options, troubleshooting, and answer pretty much any question that the user should have in the course of regular use of the program. Documentation for fellow coders or developers, on the other hand, should explain aspects of the program's operation, especially if you're not following proper conventions. All programming languages have some way to input comments or other instructions that won't actually be executed. It's also a good way to disable parts of your code, either temporarily or permanently. Mind you that commenting still takes up space inside the program file. So hefty code will either omit or assume fellow developers actually understand it, or they'll make it extremely short and only when it's strictly necessary. This used to be a major thing with coding when resources were a lot limited. And in fact, with hobby electronics, you can kind of return to that time. Comment blocks also can give correct attribution and instructions on how to run the program, including things like program dependencies. When you hear about programming, you'll often hear about Hello World. Well, that's usually the first program in most languages that somebody writes is a Hello World program, where the goal is just to print out a message stating Hello World or some variation on that to practice best program layout, implementation of one, or maybe a couple of basic instructions. Blink is kind of the Hello World equivalent for hobby electronics for when your basic hardware output's going to be an LED and you're demonstrating the output of a signal on a GPIO pin or digital pin. But if it has an onboard LED, then you might be blinking that. That way you don't have to require any other components. Now I'm going to move to Arduino, which is a very limited form of C and C++. Basically, if you work with one, you'll have an idea of how to work with the other, although there are some differences because it's tailored to microcontroller development boards. We have two methods. They're both void. We've got a setup where it does everything once and a loop where it just keeps going over again. We're going to put this in the serial monitor, so we have to first start the serial monitor at a certain baud rate. All of this will get explained in future videos. We're doing a print line. You'll notice that object-oriented nature of this. Hello world. So if everything goes well, hello world. Okay, again. Yeah, hello world. There we go. I'm doing this in Walkway Simulator, obviously. Now here we have a Raspberry Pi on Walkway, and in this case it's set to use MicroPython, which is a subset of regular Python. It's limited so that it can fit on such a small device, in the same way that Arduino is a subset of C/C++, and it's meant to fit on a small device. This is just a hello world. We got to import time because we're using a small delay to make sure that the USB gets ready, and then we're just printing hello world. Or the rest of the stuff, you got hello world. Now, new to my videos, here's a Raspberry Pi that I have that I'm going to show some programming examples on. The first one is going to be how do you do a hello world in C. Now, there are a couple of different ways to do this. We're going to use Nano Program here as a text editor. Um, yeah, I commented the hell out of this one. So you have to start with an include statement because in C, standard I/O is not just built in. You actually have to include other functions to do this. You've got a main function. Um, the int means it's returning an integer. And the only thing I'm having is doing printf hello world. And then with C, because the main is an int, you have to return 0. That means everything is all good and the program's done. So let's see how this actually is going to play out. I've already compiled the program. So let's do hello world. There we go. Got hello world. We didn't even get a new line out of that. Let's move on to C++, close C-based language. Um, let's check out the file for it. So yeah, this is a little bit different, but we still have an include statement for the IO stream. We've still got our main and all that, but our statement has changed for how to send it out. Standard C out with two left-facing arrows. Hello world return 0. Let's run this program and see what we get. Get the same thing. All right, let's see how this works with Python. Going to hello world. And in Python, it's pretty simple. Now, the thing on the top is just so I can make it directly executable. You don't strictly need that. Import sys, print hello world, and we're done. So a little bit shorter than the C and the C++ we looked at. So let's do execute it. I think. All right, hello world. And in fact, it even put the new line in there for us. Well, let's take a look at Java now. So we have a class and then we have a method inside the class. This is kind of where that object-oriented stuff comes in. So the main method to hello world, and the hello world needs to match the name of our program file, without the .java, that is. If I get into a Java video, I'll explain a lot of this better. But yeah, system.out.println, this is where that object-oriented programming comes in. Hello world, pretty simple. So we've already compiled it. So let's just run. Now the class file is the compiled code. Oh, wait. Oh, sorry, I didn't need to do that. So yeah, hello world. Actually, you know what? Let's take a look at that compiled file. I haven't done that before. See what that looks like. Yeah, this is all what it is. We could get more information if we opened hexadecimal editor, but that might be a later video. All right, let's look at JavaScript. Now, JavaScript is something different from Java. Basically, the makers of JavaScript wanted to buy Java. Java refused, and they made JavaScript. And if you're wondering, all these languages are insanely used. It's some of the most popular languages in the world, actually. Though there's a lot of others like Rust that are also popular. All right, so this one's really simple. We're just doing a console.log and the message, and it's just a console message, but it still meets the requirements for a Hello World program because it's going to print it out. There are other ways to print to the screen though. So let's see. Not mistaken. There we go. Hello World. All right, now we're going to move into PHP, which is used within HTML to essentially make it a full programming language environment. Otherwise, HTML is just markup language. It just decides how to present data. It doesn't actually process the data itself. But when we get into all of that in a later video, I'll explain more. So here's some standard PHP. I don't even have to put the HTML in. I could put this actually into an HTML file and then we could load it up, but I'm not going to do that right now. So it's just, we're just doing an echo statement with a new line, and that's it. So let's see how this goes. There you go. Hello world. Pretty simple. All right. In this case, I've made a blink program here in Walkly. We have to set a pin mode. I'm using the LED built in right over here next to the L. It's capital, so it's a constant, so it knows what to do. It'll also blink it on 13. Same time, we digital write, we set it high, so on. We wait a second, we do it to low, turn it off, wait a second, and there you go. And usually this is the first program you run on an Arduino or anything that's Arduino compatible. We're back on Walkly. Here's a Raspberry Pi Pico with MicroPython, which is a subset of Python in the same way that Arduino is a subset of C and C++. Um, we're having to import from machine, we're importing pin from time, we're importing sleep so that we can do a delay. We're setting what the LED is. This is just using the built-in value, much like LED built in for Arduino. There is a little light on here. So while true, we're setting up a loop that's just going to go over and over again. We're toggling the LED and we're doing a half-second delay. And there you go. Just to start to wrap things up, let's recap. An algorithm is a step-by-step set of instructions to perform a task. Programming is the physical implementation of that. We talked about Turing machines and Turing complete. We also talked about the difference between humans and computers. We mentioned hardware abstraction. The amount of abstraction separates the hardware from the user, so the user doesn't have to know much about the computer hardware. We talked about compilers and interpreters and how programming languages can have one, the other, or even both in some ways. The difference between coding and programming. Programming is the whole thing, while coding is just entering the programming language. We've talked about qualities with programming languages. We mentioned pseudocode and how that can help you to write a program. We've talked about conventions, grammar, syntax. We talked about comments and documentation, and also mentioning that comments in a program still take up space. We showed some examples of a hello world program. That's usually the first thing that anybody learns in a programming language. We also talked about Blink and showed two examples actually in Arduino and MicroPython, and how that's often the first program when you're working with hobby electronics development boards. Well, until next time, have a good one.